Hello and welcome back to the Research Methods and Stats Show. My apologies in advance. We have equipment issues that you cannot see this beautiful face of mine because, quite frankly, I didn't feel like setting up the camera. And I didn't feel like setting up the audience. So it is what it is, y'all. I mean, everything's broken. And one of my kids threw the camera and the microphone into the stream down the hill. So it is what it is. Today we have a very special guest, the world famous, the one and only Mick Grucock.
Hello. Pleasure to be here with you today.
Now, why don't you go ahead and tell us a little bit about yourself, Mick? I'm not sure that people know who you are.
Yes, I am a retired gentleman, and I am a novice boyer.
A what?
A boyer, but I'm just a novice.
What's a boyer?
A man who makes bows for a living, or in my case, for fun.
Oh. Okay, and I was just thinking that our show needs more expertise in boyerism.
Yes, I rather think it does.
Okay, so with that, we're going to talk about experiments today. So here are our goals and objectives today. And let me just review a couple things that are in here that didn't make it to the actual PowerPoint. These are just some corrections about your book. Your book said something kind of ridiculous, which surprised me because the authors are great and stuff, but when it comes to stats, they don't know what they're talking about. So they said that data analysis is an alternative to replication. And that was just weird to me. That's just really weird. So and they make the point that replications are difficult and expensive, so instead of doing replications, we do statistics. No, that's not the role of statistics. Thank you very much. And who cares if replications are difficult and expensive? Bad science is a whole lot more expensive. Am I right?
Oh, I assume so. I assume that you're right.
Thank you, Mr. Mick. What else is there? Oh, and your authors also said that if you look at a graphic and you plot the confidence intervals, if they overlap, they are non-significant, and if they don't overlap, they are significant, and that is actually not true. It actually turns out that it totally depends on the type of experiment you're looking at, or the type of study you're looking at. But I think a good rule of thumb is if there is 1/3 overlap with the confidence intervals, then it is borderline statistically significant. And any more overlap, it is not statistically significant. Any less, it is clearly not statistically significant. But who really cares about statistical significance anyway? Am I right? Am I right? All right, moving on. So the logic of experiments.
So remember the goals of science. We want to describe, to predict, to explain, and then, if necessary, to apply. And when we attempt to explain things, we are making causal statements. For example, we might say, does childhood abuse cause adult depression? Or does mindfulness cause a reduction in anxiety? Or does Facebook use cause jealousy? In each of these cases, we are making causal statements. And if we are making causal statements, then with what sort of validity are we concerned? Anyone? Anyone? That's right. Internal validity.
Exactly. So to establish causality, we actually need three things, if you remember. We need covariation, which means that the variable that is doing the causing should be correlated with the variable that is caused. There needs to be a time order relationship that the variable that does the causing precedes the variable that is caused. And we need to eliminate plausible alternative reasons that those two variables are correlated. Now, that last one is probably, okay, not probably, that is the most difficult to do. Pretty easy to establish a relationship. It's pretty easy to establish a time ordering sort of thing, but it's really hard to eliminate possible alternative causes. And we have tried to do that with different experimental designs. So to eliminate confounds before, we had strategies that kind of sort of worked. So what we did was we controlled for extraneous variables. For example, the example that we used was we find meat eaters and vegans who exercise the same amount, then determine the degree to which they differ in heart disease. And that strategy had its limitations. It required the user to specify in advance extraneous variables one by one. It assumes you have thought of every extraneous variable that may muck up the relationship between the IV and the DV, which that's a whole lot to think about, folks. And it can provide evidence for in the end, it can provide evidence for causation, but its evidence is much weaker than if we had used randomized experiments. So that's where the idea of a random assignment comes in. This is a much better strategy. So if people choose their groups on their own, like vegan versus meat eater, it might cause self-selection, or there might be self-selection involved and the corresponding characteristics that make them different, not the treatment itself. So if you find an observed difference, if the people were allowed to select into their groups, you don't know whether that difference is due to them, whatever characteristics made them choose to select into those groups, or if it was due to something else, like something correlated with vegan versus meat eater or whatever you're comparing. But if we assign people at random to the groups, then on average, those characteristics will balance out, which is the cool thing. So we might, for example, with the vegan versus meat eater thing, vegans tend to be more fit than meat eaters. But if you randomly assign people to be either a vegan or a meat eater, on average, the fit people will be in both groups, as well as the not so fit people. You will have an even distribution. And on average is the important thing there. And likewise, if intelligence might be a confound in a quasi-experimental design, if you do random assignment, on average, you'll have smart people in the control group and smart people in the treatment group, and not so smart people in the control and not so smart people in the treatment. So then whatever differences we observe, they can't be due to the characteristics of the group because they were randomly assigned. So that's the basic idea behind random assignment. And so instead of assuming that it was group characteristics, we assume it was the treatment. So random assignment is by far the best way to ensure internal validity.
And about that on average thing, this is an important point. So Fisher, on the left there, invented the idea of random assignment. And he very clearly said that random assignment only works on average, and there's no guarantee it will work on the first try, which is why it's so stupid, forgive the language, to say that statistics replaces replication. Statistics does not replace replication, and no amount of statistical ninja moves will make random assignment work any better than it already does. Instead, we must replicate.
Now let me pause there. That's kind of a misstatement there, and no fault of your own, Mr. Mick, because I created these PowerPoints. But you can do statistical ninja moves. You can do an ANCOVA. You can covary out the characteristic you think might muck up the relationship. And the idea there is, just in case random assignment didn't work, I'm going to control for intelligence or whatever you're covarying out. And that might work okay, but a much better way to do it is just to collect a larger sample size and allow the law of random numbers to work, which means that larger sample sizes or more replications, on average, the groups will be the same.
Right. So instead, we must replicate. Even an Ancover will not fix things. We must replicate. However, as you said, large sample sizes are an alternative. However, even large sample sizes are not a substitute for replication. So here's the basic idea. If you randomly assign 6 people, half of which are female, what are the chances all females end up in the same group? Not very likely, but not very unlikely either. Now, what if you had 10,000 people? How likely is it now that exactly half of the 10,000 people will be assigned to one group and they will all be female? Well, it's much less likely in that situation. See what happens with larger sample sizes? The larger the sample sizes, the better the chance that these characteristics will balance out.
Right, but there are still threats to internal validity. So even with random assignment, that fixes the majority of internal validity issues, but we still have threats to internal validity that exists. For example, when we are testing intact groups, we have still the threat of selection bias. So remember, this is a quasi-experimental design, which means that it isn't a true experiment. So in a quasi-experimental design, we are randomly assigning the treatment to groups, but we are not randomly assigning people to the groups, if that makes sense. So how do we address this? A better way, instead of doing a quasi-experiment, is we do a true experiment where we randomly assign... Well, of course, randomly assign people to the groups, but a better way to do, or the best way to maximize internal validity with quasi-experimental designs is we randomly assign the treatment, and then we repeat this experiment multiple times across multiple intact groups. So let's say you have a new method of teaching statistics, you have 2 classes, you randomly decide which one receives the new method of teaching statistics, and it could be that you accidentally gave the new method to the smarter class. Well, if you repeat the experiment the next semester and do randomization again, on average, that will balance out. And if it doesn't the second time, maybe it will the third time or the fourth time. You get the idea. The second threat to internal validity that is not addressed by random assignment is attrition or subject loss. And so the idea here is if you've got 2 treatments and one of the treatments makes people more likely to drop out, then the observed differences at the end may not be due to the treatment, but it might be due to the treatment and the attrition. So what can you do? Your book is wrong. Like I said, that sometimes research methods experts should not be writing about stats, and conversely, maybe stats guys shouldn't be teaching about research methods. Maybe. I hope not. So your book got this totally wrong. So your book says, I think they said something like delete people. So if there are 5 people in the experimental group that dropped out, you should delete 5 people from the control group, and that's just a bad idea. It's going to reduce power, and it's going to make it much less likely that you would detect a difference between groups. And they also said that by the time the experiment is over, there's not much you can do. You are basically screwed, and that is actually not the case. You can do things post hoc, and it's a bit sophisticated. And by the way, if y'all watch my missing data video, you know exactly how this works. And so the idea is if you measure the reason they drop out before they do, you can use statistical ninja moves, which we call multiple imputation, or some maximum likelihood methods, to estimate what they would have scored. Well, more multiple imputation is, so maximum, you don't care, but I'm going to say it anyway, just for the thousands of people who are going to comment and say, hey, blah, 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 and bark at me. Multiple imputation doesn't actually impute the missing value. I'm sorry, multiple imputation does impute the missing values, but maximum likelihood does not. But here's the idea. Multiple imputation, we estimate what they would have scored had they remained in the study. And for example, let's say that people drop out because they lack motivation. And so what do? You measure motivation before the study even begins. And then that way, when they drop out, you have measured the reason that they dropped out. And if you watch the missing data video lecture thingy, you will get exactly why you can do that. And it works great. Assuming that you have adequately controlled, quote unquote, for the cause of missingness. And then the third one is demand characteristics. So demand characteristics ain't gonna fix things. So people act how they think you want them to act. Or they might be one of them rascals and they act opposite of how you want them to act. So the best way to control this is to use a placebo and use double-blind procedures. So nobody knows what they're supposed to act like. So you would think that if they don't know how they're supposed to act, they will just act as they normally would. So with that, let's get into
Independent groups designs.
Oh, I'm sorry. Did you want to talk?
Absolutely. So in independent groups, each participant serves in only one group. So they might, for example, only serve in the treatment group and not in the control group. And so your book mentions 3 major independent groups designs. A random groups design, including block randomization, a match group design, and a natural groups design.
Right, so with a random groups design, aka randomized experiment or randomized control design or a true experiment, we randomly assign people to treatment or control conditions. That's kind of what we've been talking about a lot so far anyway. So the characteristics, generally, not always, but generally we have a very artificial environment because we want to control for every variable but the variable of interest. And so we make things super highly controlled. And another term for this is we hold constant, meaning that all factors are constant across the 2 groups except for the one variable that you're interested in observing what happens when people respond to that one variable. And these tend to be exceptionally weak in ecological validity. But this is the gold standard among psychologists. Why is that? Because we as psychologists tend to prize internal validity. We want to make sure that the causal inferences that we make are valid. And this is kind of a culture thing, I would think. And by using randomized designs, we have the best chance of retaining valid internal validity inferences. But other disciplines have different gold standards. In economics, for example, and this is kind of a misstatement. I say here that they care more about external validity, but internal validity, and that's really not the case. They very much care about internal validity. They just approach it different ways. They don't use randomized experiments as much. Instead, they use different controlling methods, instrumental variables, and those sorts of things. And they use slightly different terms, like the term of endogeneity, which we might kind of sort of equate with confounds. Anyway, they've got their own ways to handling it. And by the way, I also say that they don't care about external validity, and they actually do. But the problem, or not the problem, the advantage for them is that generally they have the population. They want to know the economics of all the countries in the world. Guess what? They have the data on the entire population. So external validity is just irrelevant at the point because they have the population. So yeah, moving on. So the strengths of randomized groups design, internal validity inferences tend to be much stronger than any other sort of design. Limitations is they are weak in external validity and they require replications and or large sample sizes. Block randomization. So this is really a strategy to use with a random groups design or random assignment. So let's say we have 4 treatment conditions. And what we do is we randomly decide the order of the treatment conditions. So in that top right image there are, for example, in this situation, there's 3, not 4. They are 3 randomly chosen orders of the experimental conditions. So condition A, B, and C in the first block, and second one is randomly chosen to be B, C, and A. Block 3 is A, C, and B, etc., etc. And so we randomly decide the order at which the experimental conditions might be administered. And then what we do is we assign people as they begin our experiment in sequence to the treatment conditions in order. So we are actually going to do this part in class and I will show you an example of that in class, and it's going to be super fun. Like, we're going to have a blast and stuff. So the benefits of block randomization. So if something happens partway through the experiment that may affect people's scores, that effect will impact the groups on average equally. So as an example, let's say we're looking at opinions on gun control, and the independent variable is 3 articles about gun control. One is written from a liberal perspective, one is written from a conservative perspective, and one is written from a factual perspective. And then partway through the experiment, something like Florida happens, or most recently, what was that? Pittsburgh, I think. So the man who fired on the Jewish synagogue, terrible tragedy, but let's say you're in the middle of the experiment and then something like that happens. And let's assume that in order you decided participants 1 through 10, as they came into the experiment, 1 through 10 were given the conservative one, 11 through 20 were then given the factual statement, and then 21 through 30 were given the liberal article. And let's assume that Florida or Pittsburgh happened at time 15, and we find that those who read liberal are more likely to support gun control. Well, what confound do we have here? Well, the problem is that even if you were to read, the problem is that what happened outside of the lab, this mass shooting, that may have influenced people's opinions, not necessarily the article itself. And so block randomization is we call this, you guys are familiar with the term, it's history as a threat to internal validity. Something happens outside the lab, and in that situation, the best way to control for that is through block randomization. And then we have a match group design, and the idea here is we identify an extraneous variable that may muck up the IV and DV relationship. And then what we do is we measure that variable, and then we sort the participants in pairs randomly into the experimental conditions. And there's an exercise. It would be nice if we could do it here, but we can't. So we're going to do that in class. Strengths of this is that with small sample sizes, this gives the experiment a higher chance of controlling for extraneous variables. Limitations, same as randomized experiments, meaning that on average this will work, but it may not necessarily work in this particular instance, and it requires replication, that sort of thing. Also, it does not control for those extraneous variables we did not think of. And what am I saying here? So for example, well, let me remain on that point. So we might decide to control on intelligence, for example, and we may not have considered that empathy is another thing that might muck up the IV and DV relationship. And so we can only control for those things that we actually think of and actually match people on. But these will be controlled for, oh, I know what I mean there. So the idea with match group is you use random assignment once you control for those things. And on average, those other extraneous variables will be controlled for over time. So if you do multiple replications, eventually it's going to all balance out. But eventually, if it's going to balance out anyway, it really doesn't pay to do a match group design. It's just extra effort, and you don't need to do it. So the best strategy always is random assignment with multiple replications. Natural groups design. Okay. So, hey, look at that.
Oh my goodness, would you look at that? I recognize that name. Dustin A. 5. Perhaps the best statistics and research methods teacher of all time. Not to mention the best scholar of all time. And might I say, is one who has read The Nexus Has Fallen. Shameless plug for you, is it not?
Oh, well, I will not stop you, and I appreciate it.
Yes, exactly. As one who has read every word of that book, I must say that it might be the best book ever written.
I am flattered. Thank you very much. So yes, that is the cover of my fiction book. And with my massive audience of about 10 people, why not leverage my YouTube to make sales of my book? Cha-ching! Gonna be rich? Probably not. So that is my book. The Nexus Has Fallen, available as a hardcover as well as Kindle on Amazon. Leave a link in the description and stuff. And I will make about 30 cents per person who purchases this book. So yeah, I'm basically going to be rich. Anyway, I will use that as an illustration, I swear. This has practical value. So in a natural groups design, this is a non-experimental design. In fact, other textbooks usually call this a non-experimental design. And what we do is we study intact groups. Now remember, with a quasi-experimental design, we had intact groups, but the variable that we were interested in, for example, we use the case of a particular type of stats teaching method, that was randomly assigned to groups, whereas in a natural groups design, the variable that we are interested is the characteristic that makes the group different. For example, smokers versus not. There are people who naturally choose to smoke and people who don't. Those are intact groups, and so we can't randomly assign the quote-unquote treatment. We can't randomly assign smokers because they're already smoking or they're already not smoking. Likewise with vegans versus meat eaters, boys versus girls, that sort of thing. So here is the practice, and that's where, okay, now I feel dumb because that book cover actually doesn't make sense unless we are doing the activity in class, which we will do. But, oh well, shameless plug. Am I right? All right, and then now down to our final section, which is statistical magic. And I know a thing or two about statistics, thank you very much. So here was the old way of doing statistics. We want to know whether the treatment works. And so what we do is we assume it doesn't work. And then we compute the probability that it didn't work. That's actually incorrectly stated. We compute the probability of observing our data if we assume that it doesn't work. Look at that. Only a year ago, I made the inverse probability error. I assumed that probability of the data given the null is the same thing as the probability of the null given the data. See, look at that. Even statisticians muck this up, and that's why NHST is so dangerous. Anyway, again, to restate that, we compute the probability of observing our data if we assume the treatment doesn't work. And if that probability is less than 0.05, we tentatively conclude there is a difference. Or the way that we put it is we assume there is statistical significance. And this way of approaching statistics we call null hypothesis significance testing, or NHST. And this way must 100% have replication, because you're playing a game of chance here. You're computing probabilities. And there might be some quirk with your data, as there always is, that made the groups look more different than they actually are, or maybe look less different than they actually are. And so, unfortunately, the old way of doing things is easily abused. So the 0.05 threshold becomes a gatekeeper that you can't even, an editor won't even send it out for reviewers unless you have a statistically significant result. And the problem is that we psychologists, not just psychologists, but across multiple disciplines in science, we place way too much faith in a p-value. And if your study does not pass that magic threshold, it is summarily rejected. But researchers are smart, so they invest in strategies that make it more likely that p is going to be less than 0.05. P-hacking, you remember that? We've already talked about this, but hey, no harm in reiterating it because it's important. So p-hacking, there are multiple ways of doing it. I've listed 3 here. There's one more in the original p-hacking article that isn't listed here, and I'll say that in a minute. So we can measure multiple dependent variables and then decide which one we're going to include, and then audition multiple dependent variables, and maybe one will give us significance, the other won't. Or we might measure multiple covariates, and then one by one audition these covariates and see if controlling for those covariates gives us a statistically significant result. Or we could test the hypothesis after the first 10 data points are collected, then after the first 20, then after the first 30, etc., etc. And the other one is that we might decide to drop an experimental condition. All the while, we have forgotten, and so this is how we abuse it, and all the while, researchers forget that NHST requires replication. So there are different types of replication if you are under a null hypothesis significance testing paradigm. One is to use exact replication, where we use the exact same experimental methods, exact same types of participants, for example, undergraduate psychology students. We use exact same statistical analyses, use exactly the same independent variable, dependent variable, and covariates. And if p less than 0.05 for study 2, we say that study 1 has been replicated. And by the way, there are a lot of statisticians out there who think it's a really dumb idea to use statistical significance as your criteria for a replication. And I will leave a link in the description to a Maxwell and Samantha Anderson, I think is her name, article where they talk about 6 different operational definitions of a replication. So that there's a big push in psychology to do much more exact replications nowadays. But there is also the idea of a partial replication, where it is slightly different from the original experimental study. And so maybe different types of participants, different statistical models, different covariates, but certain elements are the same as in the original. And then there's a conceptual replication, where we replicate the relationship between constructs, but not necessarily between the measures themselves. So an example, the original Milgram experiment, where you have a guy in a lab coat saying administer the shock to the participant in the other room, and we know that has some ethical issues, so instead you might use a different example. I think we use this at the beginning of the semester, where you bring participants into a lab and then you have them comment on YouTube videos, and you have an experimenter in a white lab coat telling you need to make rude comments on these YouTube videos. So that's a conceptual replication. You know, you're trying to establish that the presence of an authority leads people to do things they might not otherwise do, and it's just using different ways of measuring these constructs. So abuses of the old ways. Mick, you want to handle this?
Oh, absolutely. So the 0.05 threshold. Oh, yes, we already talked about that one. Let's go ahead and move along. So the new way, there's actually a lot of disagreement about what the new way of doing statistics ought to look like. In fact, there are 2 articles with approximately the same title. One called The New Statistics, and another called The New Statistics, a Bayesian perspective, if I remember correctly. So, some people say we should stop focusing so much on p-values. Others say we should continue to use p-values and insist on more replications. Or perhaps we continue to use p-values, but instead use a much smaller p-value. Others say we should focus on estimation, or on graphics, or use Bayesian statistics. And there's not much agreement about what the new statistics looks like. But what can we agree on? We can agree on, for the most part, that mechanical decisions aren't a good idea. Instead, we should use converging evidence across multiple estimates.
Yeah, and that's an intentional play on what I typically say, multiple or converging evidence across multiple studies. Why can't we use the same idea with evidential statistics? So why can't we have converging evidence across multiple estimates? So we might report a p-value, we might report a Bayes factor, we might report effect sizes, we might report, or we might use prior knowledge to inform our judgment, we might use graphical interpretation, those sorts of things. And why can't we aggregate that information together to make one informed decision rather than letting p-values hijack the decision making from us? So with that, here are our goals and objectives. I will let you pause the video and review these if you wish. Thank you all for joining us, and thank you, Mick. We will let you get back to building longbows because you are excellent at it. I don't care what people say. I don't care what you say. You keep saying you're novice, and Mick, you are the man, dude. You build bows like nobody's business.
I thank you very much for that kind remark.
And be sure to check out his YouTube channel because it is awesome. He shows you how to make some longbows, and they are very, very cool. Thank you all for joining me today. We'll see you on the next one.